Good. Check, check. Okay, guys, let's get the afternoon session going. I'm very happy to introduce our next tutor speaker, Jindřich Matoušek. Jindra is at the University of West Bohemia, which, don't ask me how, it's Czech abbreviations becomes ZCN or something like that, ZCU. So I think the Z is South and C is Czech or Moravian and So anyway, so Jindra has been there. So this Pilsen group, as it's called, first of all, they're the home of the Pilsner beer. And secondly, they're another very strong speech group. The Czech Republic is funny. There are 2 or 3 very good speech groups. One in Prague, one in Brno, one in Pilsen. And we worked with them for many years in this project, which was called PIRE. And from 2005 until 2015, Hopkins had a collaboration with them. Jindra works on speech synthesis, and therefore he's instrumental in a lot of the spoken dialogue work that gets done from their university. I can tell you a bit more about some of the more impactful projects their group has done over the years, particularly for handicapped users of Czech broadcast and so on and so forth, but I will not go into that. I'll instead let Jindra tell you more about it, and we'll look forward to his lecture. Thank you. Let's connect this back.
Yeah. Let's hope it will work again. No. No signal. I try to change to computer and back to notebook. Oh. I can try again. But it
sometimes that you disconnect this guy.
yeah, I tried now, yeah. Yeah. Okay, so thank you for a nice introduction, Sanjeev. My name is Jindra or Jindřich, it's a typical Czech name. Matoušek, I am from the Department of Cybernetics and the Research Center New Technologies for Information Society in Pilsen, University of West Bohemia in Pilsen. And my talk today will be about speech synthesis. Oh, hopefully. I did nothing. Yeah. And it will be a mix of, some older and historic methods, and also, of course, also very new methods like neural networks, of course. And it will be about models and signals, because as we will see, there are 2 possible approaches, in fact. Model-based approach and signal-based approach, and we will talk about this during this presentation. So the outline of my talk is here. After a short introduction, I will tell you some very basic details about text-to-speech technology. I believe you know it, but I will just remind some let's say, important points. And then we will talk about, first model-based approaches, historic model-based approaches like articulatory synthesis and formant synthesis. Then we switch to signal-based approach because it was very dominant during, 70s to maybe 2010, maybe 15 years. It was dominant technique which was used successfully, commercially, and so on. So we will switch to signal-based approaches, and then we will go back to model-based approaches, to statistical parametric model approaches, predecessors of neural networks, and of course, the core of the presentation will be about neural networks. I will also show some advanced techniques like end-to-end neural model-based approaches and voice cloning, which is very important and could be helpful for some people who cannot speak, for example. In the end, I will outline some future directions and I will show you some projects, TTS-related projects from our department. Okay, so we can start. As I said, there are basically two fundamental approaches across many fields: model-based approach and a signal-based approach. In the model-based approach, let's say the traditional models rely on explicit knowledge about the world, either using rules or some sophisticated knowledge representations. These models typically use mathematical or rule-based frameworks. And what is good is they allow for interpretable control over and understanding of the world around, of the system behavior. Oof. Yeah, no signal. Yeah. I have another reduction, so I can try another adapter.
You can also plug it here and just use this computer. It's the same.
Sorry?
If you want, you can just plug the USB here and use this computer.
So I will use the presentation here, but it will be from here, I understand.
No, že bys používal jako jenom tenhle jako počítač, že si to bude pak opakovat.
Tohle je přes na Google disku, takže abych to musel se přihlásit přes Google, jako asi je to složitější.
Aha, já jsem myslela, že to máš na
Ne, to je jenom...
Tak uvidíme. No, většinou, když se to vypne, tak počkej na chvilku, ono se to zapne.
Okay, so sorry for the interruption. But the model-based approach and the models themselves can be limited by simplifying assumptions and model complexity. This is the typical case is four-month synthesis. We will talk about this approach later. Or they may become overly complex and difficult to interpret or implement. And this is the case of, let's say, the true articulatory synthesis. Again, we will talk about it later. And modern approaches, modern models, this is what we use now, neural networks. They often use, large data sets and machine learning, deep machine learning techniques to learn some, very complex models, very complex relations directly from data. And yeah, this is also model-based approach, and it's a neural speech synthesis, and we will talk about neural speech synthesis in the second half of this presentation. On the other hand, there is an approach which is called a signal-based approach, and it's quite intuitive. It operates directly on some, observed data or signals in our case. And this approach in speech synthesis is typically called concatenative speech synthesis. It includes, let's say, example-based methods like diphone synthesis, or example-based methods enriched with some, dynamic data-driven methods like unit selection speech synthesis. Again, we will discuss these techniques later. Signal-based approach, it means concatenated speech synthesis, can achieve high performance by, leveraging real-world data, examples, and patterns. It's good because you use, the real entities of speech which are around us. But it offers, let's say, very limited flexibility for modification, of course. And you may struggle with generalization beyond the data which you have in your, not training data set. We don't talk about training data set in case of concatenated synthesis, but in your, source data set, in your speech unit data set, which you use for concatenation. So it's difficult to use, to synthesize new, in fact, styles and new voices from signal-based speech unit data sets. But let's start with text-to-speech technology. And first of all, I will introduce some other tasks, not only text-to-speech. I suppose you all know these technologies. You know that there is a speech recognition, automatic speech recognition, ASR. You have a recording, and you want to recognize what the recording is about. So you, for example, use a text transcription. You recognize the speech and use the text transcription, of course. The opposite approach is, in fact, speech synthesis. You have a written text, and you would like to read it aloud, I would say. So it is speech synthesis. And there are, of course, many other tasks like, speaker identification or verification. Similarly to speech recognition, you have a recording, but now you don't want to, recognize what was said, but who said it. Yeah, okay? So the result is that, for example, it's me who was younger me who was said it, okay? And as I said, there are many tasks like language identification. Again, we want to recognize not what was said, but in which language it was said, for example, Czech. And another task could be emotion recognition. So again, what was the style or the emotion present in the speech recording, like it was in a happy style and so on. So, of course, this presentation is about speech synthesis. Okay, so what is text-to-speech synthesis? What is a text-to-speech system? Everyone knows it now. I don't know, 10, 20 years ago when we lectured our students, the technology was not so known because only few systems existed and just, some gurus used it. But today everyone has a smartphone, of course, and everyone has a text-to-speech technology inside his or her, smartphone. So text-to-speech technology is known. It's a system, let's say it's a system enabling converting text to speech. We can say very simply that it's something like, talking machine which reads text automatically without human assistance, okay? And the goal is to produce speech from arbitrary text, okay? The arbitrary is important because it's not about, replaying existing recordings, but to create new speech from any text. Just a note, due to the complexity of human speech and language, it's simply not possible to store all words or even all sentences in a computer and replay them when you need to synthesize the exact word or the exact sentence. It's not possible. We must do it in some more advanced or more complex, sophisticated way. And the typical way is to use two modules: natural language processor and speech synthesizer. You can see it on the right side. The task of the natural language processing module is to convert the text to its, of course, to its pronunciation representation, basically phonemes, sequence of phonemes, pronunciation representation. And the second part is speech synthesizer. This is actually the module which is responsible for creating speech from the pronunciation representation. So very often from phonemes, from a sequence of phonemes. We will also talk about end-to-end TTS systems which are, and models which are very popular now. And in this case, there is just one module, one block. It means that the NLP and the speech synthesizer modules are joined together, and it's something like black box. Like, let's say we have just text at the input and we have speech at the output. We will also talk about speech quality of each of the methods I will present. So, what is the speech quality or synthetic speech quality? It's not so easy, but let's say we have two aspects of speech quality: intelligibility and naturalness. Intelligibility is about, if the synthetic speech or any speech is intelligible, of course, or if it is natural. So, yeah, these two aspects are basic two ones. This is the illustration of a TTS process. Today, it will be, we have a sentence from, I don't know, from some newspapers or some web page. Today, it will be overcast with showers in some areas. After 6 a.m., snow is expected. Don't panic, it's not forecast for today. Also, it looks like it could be, but there will be no snowing, I hope. in this sentence, there are some, special symbols. There is not only text in the sentence. There are some punctuations. There are punctuation marks. There are some there is a digit. There is an abbreviation. So the first step, in fact, is to transcribe this sentence into so-called, full word form. And the capital letter at the beginning can help us because it could not always, but it could mean that this is a start of a new sentence. There are some punctuation marks inside the sentence which can help us to phrase or to make phrasing of the sentence. It means we can place pauses inside the sentence, and there is a dot at the end of the sentence, which could mean that s tím nebývají problémy, jo, tady. Ještě takhle.
Jo, tady je USBčko.
Let's try another adapter. So yeah, and the dot at the end of the sentence could help us too, because it's a symbol of declarative sentence, and declarative sentence is for declarative sentences the typical intonation is decreasing towards the end, So yeah, the dot can help us. The next step is text analysis, and it's conversion to pronunciation form. So basically, what we see here is a sequence of phonemes in International Phonetic Alphabet, IPA, and it's the pronunciation form of the sentence with the punctuation marks preserved in the sentence, because these punctuation marks can help us, especially in today approaches like neural network, when neural networks are used. The next step could be, sometimes is, sometimes not, so-called prosodic analysis, which means that we can estimate, the pitch of the sentence, intonation of the sentence, and we can also, thanks to the punctuation marks, we can estimate phrasing of the sentence, and where these symbols are, we can expect there will be some pause, for example, and in the end we replace the dot with this symbol, which shows us, that the intonation will be decreasing to the end, because this is a declarative sentence. The next step then is to generate speech from this linguistic information. Today we will use some neural network, and we got some speech signal which could sound like this. Oh.
Today, it will be overcast with showers in some areas. After 6 a.m., snow is expected.
And I don't know if somebody here can understand Czech. I have also a Czech version, my language version.
Dnes bude zataženo, v některých oblastech přehánky, po 6. hodině očekáváme sněžení.
Okay, so some words about the phoneme to grapheme conversion. As I said, it's an important step because the task of G2P is to convert written language form it means text, it means sequence of letters, in fact, to a pronunciation language form, it means sequence of phonemes. And in fact, there are two basic approaches you can use. You can use dictionary, you can use rules, in fact. And you can combine them together. So typically for languages like English, we use phonetic dictionary. And we believe most words are known. Their pronunciation is known, and these words are placed in the dictionary. And the dictionary has very simple form of a word and its pronunciation, for example, using IPA or IPA phonemes, But there also must be some, rules for words which are not in the dictionary, or maybe some rules for how to concatenate words, because when you speak continuously, there could be some, aliasing or some changes in between words when you concatenate them. The second approach, which is typical for my language, for Czech and other Slovenian languages, is that you can pretty easily define some rules, and you can base your approach on rules. And words which do not obey these rules, like words of foreign origin and so on, you use dictionary for these exceptional words. So these rules could be prepared, let's say, by linguists, some expert in language, or today of course you can also train the rules using some neural network-based framework, for example. As I said, rules are meant for standard pronunciation and dictionary for exceptional pronunciation. Here are some examples of phonetic transcription in English, you know it. So these are, let's say, nice English words and the transcription. And here are some words which are, I believe, of foreign origin in English, like, Paris, Buenos Aires, or two Czech words, Čapek, the author of Error, R-U-R, and famous Czech ice hockey player Jágr. By the way, Jágr was pronounced Jagger originally in NHL, but his correct pronunciation is Jágr in English. So these words, I believe, are in every English dictionary. These two words, I think it's not so obvious that they could be in dictionary, and you must use some rules or maybe some machine learning frameworks to estimate the pronunciation of these two words. The problem is always foreign words, names, geographic places and so on. For example, my name Jindřich, it's very difficult to transcribe into IPA, IPA International Phonetic Alphabet, using English phonemes, because R is a typical Czech phoneme. I believe it's maybe the only, it occurs only in Czech language. So in English, you would say something like Jindřich, maybe, but in Czech it's Jindřich. So yeah, these are problems in every language. And a few words about prosody generation. Prosody is a very special medium, I would say. It's explicitly perceived by humans using intonation or sentence melody, or in how you use, stress pattern. Stress pattern is important, for example, in English, maybe in Russian, but not so in Czech, because in Czech it's very regular. But in English it's very important to use word stress pattern. Again, other important prosodic characteristic, how human perceive it is a variation in loudness, for example, or rhythm, tempo, and pausing and phrasing. These are important prosodic characteristics. And in speech synthesis, they are in fact modeled just using three acoustic characteristics like pitch. It's in fact F0 characteristic of fundamental frequency contour, duration of any phoneme, and energy, loudness, in fact. You know prosody has a very great impact on the naturalness, on the perceived naturalness of synthetic speech, because without prosody, it would be intelligible, but it would sound, monotonous or robotic and so on. So the prosody is very important for naturalness. In tonal languages like Chinese, it's essential because intonation affects the meaning of words in these tonal languages. So without prosody, it could be unintelligible, Okay, in the modern neural speech synthesis, mainly phrasing information, it means punctuation marks and pauses are important and are expected to be part of the phonetic input. Other prosodic characteristics in these modern methods are often modeled implicitly within the neural network framework, which is fine because we don't need error-prone, estimations of some other prosodic characteristic. So we need just sequence of phonemes and punctuation marks, commas, dots, question marks, and so on, and it's fine. The modern neural networks can work with this. Very, very, very good. This is just an example of a text processing scheme in a real TTS system, English TTS system, so just to show that it's maybe look easy, but it's not so easy to have it implemented in a system. Okay, now just 2 slides more about speech synthesis evaluation. I said that it's important, or when we evaluate synthetic speech, we have 2 aspects. Intelligibility and naturalness, right? But when you are working in the ASR field, you have some automatic measures like accuracy and so on. So why don't use such metrics also in text-to-speech synthesis? Because it's difficult. Due to the complexity of speech and differences in human perception, the objective evaluation is really difficult. And in fact, no universal objective metric exists for overall speech quality up to date. So there are some common objective measures like, Merkel-Strahl distortion, perceptual evaluation of speech quality, short time intelligibility, or some measures like signal-to-noise ratio and signal-to-distortion ratio and so on. But these metrics often correlate poorly with human perception. But they could be useful for some, benchmarking your system for preliminary versions and for system development. You can use it because they sometimes are helpful. But if you want to completely evaluate how your system is good, you need a subjective listening test, and they remain essential for this target. Let's say that recent attempts were trying to reborn some efforts to measure quality of synthetic speech automatically. There were some, voice moss challenges 3 years ago, and some systems, some teams achieves, let's say, very promising results. This is the right word, like UTMOS system or our system, our ensemble system, but still it was very tailored to the concrete task, specific task, which was in the challenge when you try to take the train neural network and evaluate some other synthetic speech, which was not included, in training data. It could be a problem. So, yeah. Still, we need listening tests for some, reasonable evaluation of a system. What does it mean? It's a subjective quality assessment by human listeners, nothing more, You need many listeners. Let's say 30 listeners and more are recommended. Then the subjective evaluation may become more objective, let's say. But it's not easy to have such many listeners. you may know some automatic, frameworks, or not automatic, but some frameworks like Amazon Mechanical Turk, I believe, or some other crowd sources websites where you can pay people for evaluating the synthetic sentences, but it's not so feasible for universities, I would say, and you have to you have to check the results because the people are paid for, so you must check that they are good at this task and not just trying to answer just trying to guessing the evaluation. So it's not easy to have many listeners. You can ask the guys from our department when there are some deadlines on conferences and we need some listening tests to evaluate our let's say, novel method. They don't talk to us because they don't want to make so many tests. So yeah. What I'm trying to say is that listening tests are essential, but they are not. It's not easy to have listeners to make the listening test. So definitely, it's good idea to work on automatic evaluation frameworks, and we believe that it will be better and better in the future. But still now you use listening tests. And two kinds of listening tests are used, intelligibility test and naturalness test, right? The intelligibility tests the main two kinds of intelligibility tests are modified rhyme tests, which is a group of words differing in a single phoneme, like fang, bang, rang, hang, gang, sang. You play you play one word to the listener, and he or she, choose the right one from this list. The first option, the second option is to use so-called semantically unpredictable sentences, like these are phrases that are grammatically correct but have a meaning that is not readily apparent or cannot be easily guessed on the words or the context, like the sentence, "How shall a milk force the umbrella?" Let's say when you play this sentence to the listeners, and when a listener, for example, miss the word milk, it's very difficult to guess the word based on the context. But the sentence is grammatically correct. Let's say that intelligibility tests are not so common today because every new system, and there are many new models every month. In today's world, we suppose that any model can produce, intelligible speech, and it's mainly about the naturalness. What is it, naturalness? It's quite vague. It's quite unclear definition of naturalness. Let's say it's something like how human-like the synthetic speech is. Does the speech really sound like from a human being? And three tests are typically used: mean opinion score, MOS, which is the task when a listener is listening to a synthetic sentence, and they can evaluate it on a 5-point Likert scale. It means 1 is the worst, 5 is the best, and when you have many listeners and many sentences, you can average the evaluation, and you got some real number between 1 and 5. With numbers very close to 5 should be, in fact, a natural speech, and numbers close to 1 should be totally robotic or totally bad speech. Another type is Mushra, which is a concurrent comparison of several synthetic samples. Here is an example. You can hear or listen to various examples of the same synthetic sentence from different systems. Very often also a reference, natural speech, is included in this selection, and you just, you evaluate these examples side by side. And the last one is paired preference test, which is, I like this test because it's, let's say, easy for the listeners. You just compare two stimuli of two systems or baseline and a new version of your system, and you can compare it on 5-point scale. For example, when A is much better than B, or A is better than B, or A is the same as the B, A is worse, or A is much worse than the sample B, you know? And the 3 scale is just A is better, A is the same, or A is worse than the sample B. Well, now I can introduce the speech synthesis technology timeline. You can see that here are some blocks or some periods in time where model-based approach was dominated or where signal-based approach was dominated. And we can now go through these epochs and we will end in the modern era. So I will start with some which I call zeroth generation models. It will be very old approaches, model-based approaches like articulatory synthesis and electronic synthesis. And talking about articulatory synthesis, we should recall how a human produces speech. So very simply, very simplified. There are lungs, and lungs is the origin of speech. The air from lungs is going to voice box. In the voice box, there are vocal folds which vibrate with some frequency. This is the fundamental frequency of voice. And from the vocal folds, the signal with this fundamental frequency is going through vocal tract cavities. In these cavities, new resonance frequencies, also called formants, arise due to the physical features of the cavities, and in the end, and you use also some articulators like tongue, teeth, lips, and in the end, the speech signal is radiated to the surrounding. Yeah, so this is very simply how a human produces speech, and the articulated synthesis itself tries to mimic the human speech production process as I explained now. So the articulated synthesis tries to simulate movements and interactions of articulators, vocal folds, and so on. In fact, very often articulatory models were physical or physiological models of the vocal tract. The problem is that it requires extensive knowledge of speech anatomy and articulatory phonetics, and it's very complex and difficult. So, in fact, articulated synthesis or system-based or articulatory synthesis hasn't been used in practical real-world speech synthesis applications. This is an example of an articulatory synthesis model called talking machine from von Kempelen. It was a mechanical model. I will not go into details. I just try to show an example.
He, ha, who, ha, da, da. Mama. Papa. Mama. Mama.
So very historic model, mechanical model, which they say it could produce any word of English. I'm not sure, but yeah, this was the start of speech synthesis. In fact, at the beginning of 20th century, there was an era of still articulatory models, I would say, but not mechanical, but electronics models, electronic circuits, and so on. And a very famous system from, let's say, the 1930s is Voder. It was some machine very resembling later Forman synthesis principle, but it was, let's say, still articulated model because it was, it was a machine and some, skilled operator had to, drive this machine. Here's an example.
To evening audience, to afternoon audience.
This may be a little bit more intelligible. It was good evening radio audience and good afternoon radio audience, right?
To evening audience, to afternoon audience.
Okay, so it was, let's say, Zero's generation of models. What I now show as first generation models, it's, they are Forman synthesizers. Forman synthesis is first, let's say, approach which uses computers or something like computers in 1950s, digital approach. And its principle was quite intuitive. The goal was to produce speech segments by generating artificial signals based on a set of rules that mimicked the Forman structure. It means the resonance frequencies in vocal tract of natural speech. And it was based on a so-called source filter theory. The source filter theory is, model is shown here. The left part is about the excitation. This is the source part, the excitation. These are the voice sounds, these are the unvoiced sounds, and this is the filter. It means vocal tract filter. And when you designed, special rules how each Forman for each phoneme should look like, you could end up with something which was quite intelligible in that time. The advantages of this approach were that it was highly intelligible with constant quality, and from the point of view of today, it was well suited for embedded systems. Embedded system at that time with limited memory and computation power. It was not computationally demanding. The limitations were, unfortunately, it was not natural. It produced artificial, robotic-sounding speech, far from human speech. And it was difficult to design rules. Experts had to do that. For many years, maybe 3 to 5 years, they had to, tune the rules for the system to be intelligible. Some examples of speech synthesis system from that time: parametric artificial talker from the University of Edinburgh.
What did you say before that? Telepathy. What is your
And famous OV system from Gunnar Fant.
How are you? I love you.
Okay. And this slide is about, late Forman synthesis because this approach to speech synthesis was still with us in, let's say, late 1890s. And it was, in fact, a first commercially successful system. It was, you have some examples of mid-talk, lat-talk, deck-talk. These were systems that were designed by Dennis Claude, another famous person in speech synthesis. And you can see the structure of the model here. Again, it's a source filter model. This is, this is the source. This is the vocal tract model with this branch being responsible for synthesizing vowels, and this branch is responsible for synthesizing, consonants. And I will show you an example from 1980s. And I would like to say that with some changes in parameters, which was not easy, but you can change parameters of this model, and the system speaks in another voice. This is very, very similar to what we are doing now today with neural networks when we fine-tuning them on other, domain or other voice. But in 1980s, this quality was quite good, I would say.
I am perfect Paul, the standard male voice.
I am beautiful Betty, the standard female voice. Some people think I sound a bit like a man.
I am huge Harry, a very large person with a deep voice. I can serve as an authority figure.
My name is Kit the Kid, and I am about 10 years old. Do I sound like a boy or a girl?
I am Whispering Wendy, and have a very friendly voice quality. Can you understand me even though I am whispering?
So this was, I would say, very first commercial successful system, DickTalk. Okay. And now change. We changed to signal-based approaches because format synthesis was nice, was okay in that time, but it was still robotic, and there was still you search for new possible ways how to increase the quality of speech synthesis. So there was a switch to signals. The idea was quite simple. Why bother modeling speech if we can use real speech signals? We can record speech signals and we can use it. Why to model them? What could be better than replaying actual speech recordings? These are the natural recordings. We can use them. So this was the idea, and the intuition was that, and it's true. Speech is composed of smaller units, let's say phonemes, for example, and the speech we record, the recorded speech, can be segmented into these phonemes-like units and store them to a database. And synthetic speech can be produced easily then by recombining and concatenating these units, these speech fragments from this database. Okay? And by design, the synthetic speech should mimic the voice of the source speaker. It was not guaranteed in format synthesis. And here, from principle, you should obtain the same voice, the same voice identity as as the speaker who recorded, the recordings. It's a signal-based approach. It's also called concatenative synthesis because the speech was created by concatenation of short speech units. The principle I also said was that a potentially very large database of short, high-quality speech fragments is created from high-quality recordings of a single speaker. And these speech fragments could be then recombined to form synthetic utterances. So we do not generate, in fact, as we know it today, we don't generate the speech, we just recombine existing speech samples, we don't use models, and we can concatenate them, and it worked in that time. The advantages is it's intuitive, it's straightforward approach, it's, let's say, more engineering approach. Why model speech if we can use real speech, right? And indeed, with a sufficiently large database, we can achieve very high quality, but for the specific voice and specific speaking style, which was in the recordings, of course. And another advantage is that concatenated speech synthesis preserves speaker identity and prosodic details inherent in the recordings. Of course, there are limitations. This approach requires huge databases and extensive manual preparation. To prepare nice speech unit database, many people, manpower was involved, so it was time demanding and costly. And databases usually had to be recorded specifically for this purpose, very, very carefully recorded. So pre-existing recordings were rarely suitable. You had to record database for this purpose, of course. This approach is also limited in flexibility. It's difficult, of course, to modify voice characteristics, style, or add some expressive emotional content because it was not recorded in the source recordings. So changing to a different voice or speaking style is possible, but usually it requires recording an entirely new database in the desired style, in the desired voice, and it's costly and time-consuming. And from principle, inherently, this approach may suffer from audible discontinuities between units because you concatenate them. And when you concatenate some units from different sentences, this is always, a possible source of problems. But it worked sometime. The first generation of signal-based approaches was so-called diphone synthesis. Why diphone? Because the speech unit was not phoneme, in fact, but diphone. Diphone is a speech unit that starts in the middle of one phoneme and ends in the middle of the next phoneme. Okay, but it was the same. It is of the same length as phoneme, but it started in middle of one phoneme and ended in the middle of the next phoneme. That's why it was called diphone synthesis. But in fact, we can say that we can also call it something like single unit instance synthesis. When I will be talking about unit selection, I will repeat this. Okay, so we had some recordings, very few recordings, let's say, less than 1 hour, and we have some speech unit database. We had to segment the sentence into diphones, or phoneme-like unit. Segment means that you find where each diphone begins and ends. And these speech fragments are then placed into speech unit database. Then we have some specification what should be synthesized. Typically, in this kind of synthesis, of course, we had phonetic transcription or what sequence of phoneme, what should be synthesized. And in addition, we also had, some duration specification of how long each diphone or phoneme, in this case, should be long. And we have some pitch contour, F0 contour, how the intonation should evolve during the sentence. And using these specifications, we took each unit from the database. We had to modify it prosodically because in the database, the aim was to have the most neutral instance of each speech unit in the database so that we can modify their prosodic features easily. And then we just concatenate these speech fragments, and it could sound like this.
Alan is happy to introduce you to its high-quality text-to-speech.
An example of a Czech version.
Zavírání na záchody nebo do komory mezi hračky, někdy i fyzické tresty. Takové byly podle rodičů výchovné metody v jedné z olomouckých mateřských škol.
So to summarize this, in the speech unit database, for each diphone there was just a single instance. Very average, very monotonous instance. And it worked because the quality was, let's say, solid compared to 4-month synthesis. And the memory footprint and the computation was also low, and it worked for some time. The next logical step was, and I call it second generation signal-based approach, was unit selection synthesis. The principle here is very similar to diphone synthesis or to single unit instance synthesis. But now we have many, many recordings, not just few, but many, let's say more than 10 hours of speech. And we, again, the first step is again to segment these utterances, these recordings to phoneme-like units. And because there are many, many recordings now, these segmentations were automatic. So again, we segmented this time automatically the source sentences, and in the speech unit database now we had many, many instances of each speech unit, of each phoneme. Not just one, but many. Maybe for A, we could have hundreds or rather thousands of instances of phoneme A. And the trick was, again, we had some specification what should be synthesized. Now we also had some linguistic description of what should be synthesized. Some, let's say it's called sometimes symbolic representation. We had what should be synthesized. What is the current phoneme, previous phoneme, next phoneme, which is the position in a syllable of this phoneme, which is the position in a word in this phoneme, what is the position in a sentence of in this phoneme, what is the phrase type, let's say this is the phrase type with dot at the end, declarative sentence, just here a dot, and many, many more features, linguistic features you can use here. And now, because in the speech unit database there are many instances of each speech unit, in real time, dynamically, it was about to select the best units which, according to some criteria, Viterbi search was often used for this task. So, in fact, from all possible concatenations, let's say easily, we according to some criteria, we selected the most or the best sequence of speech units. This is the difference between diphone synthesis and unit selection concatenative synthesis. And again, we concatenated the result, and it sounded like this.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
It's an example of a Google unit selection system.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
And again, a Czech example.
Tohle je ukázka syntézy řeči výběrem jednotek.
Okay, so it was unit selection. It sounded quite good for some. It was very successful in commercial systems. But then another change was back to the models. Why? Despite the success of signal-based models and commercial success of this of signal-based models, concretely unit selection speech synthesis, still synthetic speech is not perfect. It's not close to human speech because, as I said, concatenation points are potential sources of audible artifacts or discontinuities. It was virtually impossible to change the voice or speaking style of the produced speech without recording entirely new database. It was bad from this point of view. And another reason was that preparing the data, it means recording and segmented speech, requires strong human intervention, and it's time consuming. It was not so easy as it is now when you use some modern model approaches, So the model-based approach was revisited, and it resulted in statistical parametric speech synthesis. In this model approach, model-based approach, speech is modeled again using, but now statistically models. Statistically is modeled, not by rules. Yeah, this is the difference between signal-based approaches when the speech is, created by manipulating recorded units. hidden Markov models, HMMs, and later deep neural networks were used as the statistical models. This approach does not operate on speech units, as I saw, at the raw signal level, but rather models their statistical properties. So these approaches worked on unit level, but models their statistical properties. And speech is then synthesized from these models, not directly from database fragments. So signals are used just to train the models and not for the creation of synthetic speech. So we now have the third generation of models, which is called also statistical parametric synthesis, or HMM, or DNN synthesis. The principle is, as I said, this approach uses learning-based parametric models, HMMs or DNNs, and all information required for speech generation is stored in these parameters of the models. So there is no need for explicit speech segments during synthesis. And speech is generated statistically using statistical frameworks. So it models, acoustic features and then reconstructs speech from these parameters. Advantages: lower data requirements, smaller data sets than in very successful unit selection synthesis. Can utilize pre-existing data sets and speech recordings. It's more flexible. It's relatively easy to change voice characteristics by modifying model parameters. You can change model parameters and the resulting speech sounds different. And can generate speech for unseen speakers or speaking styles through parameter adaptations. You can adapt, today we would say, fine-tune the parameters to another speaking style or another voice. Limitations, of course: it generally produces less natural and less intelligible speech, I mean statistical parametric speech synthesis, than unit selection TTS. And the synthetic speech often sounds, something like muffled or over smooth due to the statistical modeling, because statistical modeling is about, averaging. A scheme of HMM-based speech synthesis. Again, we have some specification of what should be synthesized, very similar to that we showed in unit selection. So we have, again, some sequence of phonemes like dog, and you have some other linguistic features like previous phoneme, next phoneme, positions label, is this phoneme under word stress, and so on. Now we have a database of context-dependent models. The context-dependent models are, phoneme-like models, but with context. And these models were trained on real speech data, and their parameters were optimized in some way. And during inference, we just pick up each model and concatenate them, not speech signals, but models concatenate. And each model produces some acoustic characteristics like, F0 or something like speech spectrum. And this acoustic characteristics can be then converted to speech using some synthesis filter. Today we will say more vocoder, but at that time it was synthesis filter, and you have some output, some signal at the output, and it sounded like this.
After years of preparation, thousands of athletes are preparing for the biggest moment of their sporting lives. They are preparing for the Olympic Games.
Oh, check. Oh. No.
Tohle je ukázka statistické parametrické syntézy řeči.
So, it was not better than unit selection, but it had some other advantages, like, you could change parameters of the models and synthesize speech in different style or different voice. And it can be seen as an intermediate step towards neural synthesis. The next step was not the neural speech synthesis as we know it today, but it was just about replacing HMMs with neural network. Okay, so in the next the next step was very similar to HMM-based speech synthesis. Again, we can see that the input specification is the same, but now instead of HMMs, we use neural network, and we also could use, some explicit intonation patterns like F0 and so on. And the neural network now predict acoustic parameters from the linguistic input. So again, there are some acoustic parameters similarly to HMM-based speech synthesis, and there is some vocoder. Now it's called really vocoder. It's a signal-based vocoder, not neural network. And from the vocoder, again, the output of the vocoder is speech signal. And it could sound like this.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
Tohle je ukázka syntézy řeči pomocí jednodušší neuronové sítě.
So this approach could be seen as an intermediate step towards full neural speech synthesis. And here we go. The fourth generation of models is neural speech synthesis. It was, in fact, a logical step from HMM and DNN-based speech synthesis, because it was a move from, traditional parametric synthesis models to more powerful neural network models, which now models not only acoustic representation, but the whole process of generating speech. These are the modern neural networks. And you know that neural networks are used in many fields, and they were used before, they had been used before they were used in speech synthesis. So the inspiration was the success of these neural architectures concretely at that time. Convolutional networks and RNN networks like LSTMs in computer vision especially, and NLP fields. This method, complete neural network approach, I would say, enable also end-to-end learning and capture complex dependencies in speech data, which were not possible using much simpler, HMMs. And neural synthesis really brings in significant improvements, not only to speech synthesis, but also in other fields. But in speech synthesis, in naturalness, expressiveness, and flexibility compared to previous generation models like HMMs. And for the first time, it's important, this modern model-based approach surprised signal-based approaches like unit selection. For the first time, it was better than the best unit selection that was available at that time. And importantly, neural synthesis has simplified access to speech synthesis and its commercialization. So, there was a leading, it led to a boom of startups like, 11 Labs, which use TTS across different diverse domains. So many startups and many institutions started to work in speech synthesis because of neural network, because they can use such a framework which can be transferable from their domains to speech synthesis and so on. So the principle is quite easy, quite clean. Neural speech synthesis is in fact a special class of statistical parametric models in some view, based on deep neural networks, which model the whole process of speech creation. And often relies on modern generative models like GANs, flow-based architectures, diffusion models. The advantage is there is a huge improvement in speech quality in terms of both intelligibility and naturalness, of course. This is the most this is the bigger advantage, I would say, increase in the quality. It requires less human preprocessing and feature engineering because many aspects of speech can be now learned automatically from data using neural networks. It's highly flexible. It can generate a wide variety of voices, speaking styles, and emotions, expressions using, different fine-tuning schemes and so on. So it's very flexible. There are also some limitations, of course. So everybody knows it's very data hungry. Large, high-quality data sets are needed for training, especially when you train some speech foundation model, I would say, or some voice from scratch. Training and inference are computationally demanding and costly. Especially training requires significant GPU resources. You can train on CPU, I guess, but it will be not feasible. But another limitation could be viewed that there is a risk of overfitting or artifacts if the training data is insufficient or unbalanced. So as in any field, you must have very good data set, very good database, which covers all the aspects you are trying to model to have good results. Okay. WaveNet. WaveNet, it's the neural network which started the boom of neural speech synthesis. Again, I try some very simplified scheme. Again, we have some input linguistic representation, specification at the input, similar to HMM-based speech synthesis. Then there is a neural network based on convolution principle, dilated convolution, and in the end, you have speech samples which are at the output of this network. It's quite interesting that it was the first time some neural network generated speech samples directly, not acoustic representation. And it was because they say that WaveNet was created or was designed in Google, DeepMind, and they were inspired by the principles of pixel CNN from computer vision. And everybody who worked at that time in speech synthesis thought it was impossible to generate speech samples directly from a neural network. But these guys were from the computer vision field, and nobody told them it's not possible, then tried and it was possible. So it was a fresh view on using neural networks, models, and architectures in this field. It's an autoregressive model. It means that to generate a sample, you need some previous samples. And it was the most painful for this approach because it was very slow. It was, let's say, almost 60 times slower than real time, the first version of WaveNet. But it was very good. The quality was very good. Yeah, this example, Google. Cannot click on it. What's yeah. Oh. Now I will show an example of a very interesting thing. As I said, the WaveNet was autoregressive. It means that when you just get the first sample, and it will use the sample to generate another sample, and the previous samples to generate another sample and another sample. But to get intelligible speech, you have to condition the input not only on the sample but also on linguistic information like phonemes and some other specification. When you don't do this and you use just the sample and the next sample will be generated based on the previous sample and the next sample on previous two samples, it will result in something like which sounds like a human speech, but it's not intelligible. This is the example.
Sådan. It was fantastic, yeah. Jag står ser man på den plötsligt när ni sitter och gör det för den där går kunde det så. I'm plus.
So it mimics human speech, but it's totally not intelligible because there was no linguistic conditioning. I try the right sample. Yeah, now. So no. So we skip the example of WaveNet. Okay, and now to the modern era of using neural networks for speech synthesis. The basic blocks are the same as I showed you at the beginning of my presentation. There is a text analysis block, which convert text to some linguistic features. Today, phonemes with punctuation marks preserved are used, typically, but you can use also some more rich linguistic features. But it works pretty nice if you use just phonemes. This is text analysis. Then there is acoustic model. Acoustic model, there is linguistic features, phonemes at the input, and there are some acoustic features like MEL spectrograms at the output. Okay, and another module is vocoder, which has acoustic features at the input, and the acoustic features are typically MEL spectrograms, and speech waveform samples of speech are at the output. Okay, so typically the traditional scheme of today neural networks is that we use two neural networks. One is acoustic model, and the second one is vocoder. Okay. As for text processing in neural TTS, I just repeat that thanks to the large modeling capacity of modern neural networks, the neural TTS system typically use as input only a sequence of phonemes. Rich linguistic information like position in word and position in sentence and so on is not really needed anymore. Just we have to preserve the punctuation marks in the sentence to know where the pauses are, what is the kind of the sentence, dot or question mark at the end, and so on. The text analysis is also very simplified. In fact, it just includes text normalization, like converting text to its full form, and still it's good to perform to conduct G2P, phonetic transcription. No other linguistic features are usually needed today. So the text is represented by a sequence of phonemes, and punctuation marks are preserved. Prosodic features like intonation, duration, rhythm, pausing, and so on are today typically modeled directly within the speech generation model, within the neural network. There is no need to have them, some contour of F0 is not needed now to be at the input of the model. And very often today, some pre-trained text or phonetic models are used. These models are pre-trained of massive amount of text or phonemes that can capture implicit phonetic and prosodic information and leverage it during text processing for speech synthesis. These pre-trained models can enrich the input sentence in inference with some knowledge which was learned from many megabytes, gigabytes of text. Some kinds of models that use it are phoneme level BERT, for example, PL BERT or X-phone BERT. Any model architecture, any model structure can be used in speech synthesis, like classical DNN or convolutional CNN, recurrent RNN, LSTM, and other variants of RNN, self-attention-like transformer, of course, sequence-to-sequence architectures like encoder, decoder, of course. And in speech synthesis, very important is to use modern deep generative models like autoregressive models, normalizing flows, variation autoencoders, diffusion models, generative adversarial networks. It's not a model, it's a framework, let's say. So these structures and architectures are used in very different models in speech synthesis now. Sorry. I will continue with this two-stage approach. So some illustration of this process is quite easy. Still, we have phonemes at the input. We have speech waveform at the output. And the first step is to use acoustic model, which converts, predict from the sequence of phonemes, predict the acoustic representation, which is very often MEL spectrogram. And the MEL spectrogram is then fed at the input of the vocoder. The vocoder could be WaveNet. WaveNet is still used as a vocoder, not as a TTS system as a whole, but as a vocoder. And when it has MEL spectrum at the input or some other vocoder like hi-fi GANs we will show, we have this vocoder then convert the MEL spectrogram to the sequence of samples, waveform. Of course, we have to train each of the modules. So in the case of acoustic model, we train it on a pairs of sequence of phonemes and the corresponding MEL spectrograms. And in the case of vocoder, we train it on the pairs of MEL spectrograms and speech waveforms, of course. Yeah. And it could sound like this, hopefully. Yeah.
The Blue Lagoon is a 1980 American romance adventure film.
And the Czech example. No, yeah.
Tohle je ukázka syntézy řeči pomocí složité neuronové sítě.
Many acoustic models are available. Here are just some, I would say, the most popular ones, like Tachotron, Deep Voice, Fast Speech, Glow TTS, or Diff TTS. And we can say just a few words about Tachotron, which was and still is being taken as a benchmark for speech quality. Again, it's a system from Google. It's autoregressive encoder attention decoder model. It has, encoder. It has a decoder. I will not go into details. It uses WaveNet as the vocoder. So Tachotron itself is an acoustic model. And it uses, when we get or take vocoder WaveNet, at the end of the acoustic model, we can generate speech samples because Tachotron, as we know it, generate MEL spectrograms. Sorry?
I wanted to ask for the acoustic model and the vocoder.
Okay.
Jointly trained?
I will say it. In fact, in the two-stage model, they are trained separately. They are separately. I will go to this point later. As you know, you train this one separately, and you train this one separately. But I will take this point later. Well, so this is Tachotron, and this is it was I don't know, it was 218, I think, the year. Yeah. This paper and this model was published, and it was very good. It was significant improvement in synthetic speech quality, let's say, over WaveNet. And this is the example of tachotron with WaveNet.
This is your personal assistant, Google Home.
Okay, and just to show you some overview of acoustic models which are used, not every acoustic model is here. You can see the dynamic development in this area in the field of acoustic models. So these acoustic models were used and arose from, I don't know, 2000 and 2018. So many models and new models counting. The vocoder. This is the second module of the two-stage model, two-stage approach are vocoders. So some popular vocoders are here: WaveNet, WaveRNN, Hi-Fi GAN, Melgan, WaveGlow, WaveGrad, IST, FTNet, and many more. Maybe the most successful and most popular is Hi-Fi GAN. I don't know, Hi-Fi GAN or Hi-Fi GAN? Hi-Fi GAN, I think, Hi-Fi GAN. It's based on very known generative adversarial network framework. It uses generator and discriminator. The generator is, in fact, here. It's based on convolution architecture. And the discriminator, and the generator tries to generate as best speech samples as it can. Discriminator is, in fact, a binary classifier, real or fake. It, in fact, uses two discriminators. It's not just a single discriminator, like two discriminators are used, multi-scale and multi-periodic. And adversarial training is used here, is employed. And you know what is it, adversarial training. Generator tries to generate waveforms that fool into thinking they are real, that fool discriminator into thinking they are real. And on the other hand, discriminator learns to distinguish between fake, it means generated speech, and the real speech, okay? And this is the principle of Hi-Fi GAN, which is used as a vocoder in many systems. Example of a Hi-Fi GAN output.
An examination of this report shows how even the most insignificant township had its jail.
Okay. And again, some overview of many vocoders which were proposed and designed. To overview the two-stage approach in neural TTS, the principle is that the two-stage speech generation is text to milspec, first stage, and the second stage is from milspec to waveform. The advantage is that these two models, let's say simpler models, are trained independently. It's separately. And in fact, compatible acoustic models and vocoders can be combined. So you can use acoustic models and try to use some other vocoder, combine them, and you have a new network. In fact, you know, limitations is the that they are trained separately. This is the limitation because the training two models is not optimal. It's not optimal. Why? Because TTS is text or phonemes to wave problem, and here we train text to milspec and milspec to wave. So it's not optimal, definitely. And also there is an inference mismatch because vocoders are typically trained on real MEL spectrograms, because we can then combine them with different acoustic models. But during inference, the vocoders they are not real spectrograms, in fact, at the input of vocoders, but they are just predicted MEL spectrograms at the input. So there could be some mismatch between real and predicted generated MEL spectrograms. And this is a limitation. Okay, we continue, and now we will speak about end-to-end speech synthesis. I don't know if it is still fourth generation or maybe already fifth generation. What is it, end-to-end speech synthesis? We can say it's not two-stage, but one-stage modeling. Again, very known scheme, and now end-to-end. What is it end-to-end? The true end-to-end, or also full end-to-end, is this. Just one big neural network with text in the input, and speech waveform at the output. It's full end-to-end. But very often you can hear about end-to-end, and it's this. Linguistic features or phonemes at the input, and a single complex neural network with speech waveform at the output. But still, there is a text analysis module which is not included in this end-to-end. And this is maybe the most frequent use now, end-to-end. But it should be, the full end-to-end is the first case, you know. Challenges in end-to-end neural synthesis, of course, training. Training is demanding. It must bridge different modalities like text, discrete symbols, or phonemes, discrete symbols, versus speech, which is, in fact, continuous waveform. So there are some mismatches between lengths of these modalities, because when you have a 5-second long utterance, it could consist of, 10 words, maybe 50 phonemes, and let's say 120,000 of speech samples also correspond to this length at this signal level. So there is mismatch between lengths 50 versus 100,000. And there are some memory limitations because they are these are very complex networks. They are typically not possible on, at least on hardware we can achieve, we can reach. It's not typically possible to use the entire utterance, all speech samples of a sentence at once for modeling, so we had to, use some shorter segments. But when you use shorter segments, it can suffer from, some limited context, so it can limit model performance. So there are some challenges with training and computation. Again, some scheme of the end-to-end or one-stage approach. This is the two-stage approach we showed earlier. Now, these two models became one model, one network, in fact. And we don't use Mel spectrograms anymore explicitly. This representation is not needed because this representation is hidden somewhere here. It's a latent representation. And it could be, in fact, Mel spectrogram, but it couldn't. It mustn't, you understand me. It could be a Mel spectrogram or not. And it doesn't matter what is it because it's trained, it's a latent representation, it's trained, it's optimized within the network. So we don't fix some intermediate step to Mel spectrograms. Why? Mel spectrograms. And it's trained within the network, okay? So the whole process of phonemes to speech is now trained and optimized. Of course, the training, for training we need pairs of, let's say, phonemes and speech waveforms, no spectrograms, of course. Some example of end-to-end neural network. Once more.
This is an example of speech synthesis when an end-to-end approach is used.
An example, check. I must play check.
Tohle je ukázka syntézy řeči, když použijeme Sakumpradům přístup.
And some popular end-to-end models are, or maybe the first one was Clarinet, fast speech QS. It's a kind of fast speech acoustic model with a vocoder. So together it is end-to-end system. Width, natural speech, all style TTS. These are popular end-to-end models. I have here some example of such a complex end-to-end system, which is called style TTS. This is the training scheme. It is a very complex model with 4 pre-trained networks, like, it uses some pre-trained phoneme level BERT for better phonetic representation. It uses text aligner for phoneme to MEL spectrogram alignment. The MEL spectrogram is used inside the network. It's not a fixed representation. It has some pitch extractor to estimate, the F0, the pitch contour during a sentence. And it has also some wave language, wave LM for, as a discriminator to judge whether the predicted speech is good enough, let's say. This system learns to infer the most appropriate speaking style from phonemes. That's the name, style TTS. It uses diffusion, a generative model, to generate speaking styles, something like acoustic or speech timbre, or voice timbre style, or prosodic style, like several prosodic features. It has a duration and prosodic predictor, and it also uses discriminators we know from hi-fi GAN to discriminate, to evaluate how the speech is good during training. And in the inference, it uses trained acoustic text encoder to extract phonetic representation from input phonemes, prosodic text encoder, PL-BERT, to extract rich contextual prosodic embedding for style sampling, because style sampling is sampled from this rich prosodic information. Prosodic predictor is there, and it's predict prosodic characteristics directly from PL-BERT and prosodic style representations. Hi-fi GAN or IST-FET-net are used as one or the second are used as decoder in the system here. So in fact, there is a vocoder, but it's an integral part of the whole model, not separate, okay? And the decoder input is time-aligned phoneme representation, predicted prosodic features, acoustic style, and the output is the speech waveform. And the example of a style TTS output is here.
In this paper, we present style TTS2, a text-to-speech model that leverages style diffusion and adversarial training with large speech language models to achieve human-level text-to-speech synthesis.
Okay. Some overview of other end-to-end models is given here. By the way, I use this wonderful book, text-to-speech, neural text-to-speech synthesis from, I don't know, Xiao Tan. I don't know. I'm not sure now with the pronunciation, but it's a very, very good book from 2023, Springer. So these models, the model overview and so on, I use from this book. Okay, so the principle of end-to-end approach in neural TTS, it's one-stage speech generation from phonemes or text to waveform directly, okay? The advantages are direct optimization for the final goal, no split between two neural networks, one complex neural network, and we optimize it for the final goal, which is text to waveform. It reduces, of course, the errors or incompatibilities from the two-stage training and inference. Being an end-to-end, it requires less expert annotation and feature engineering. For example, we do not need external phoneme-to-speech alignments. The alignments are learned during the training. There is no fixing, no bias towards MEL spectrogram representation. As I said, we can use some, there can be some other representation which is hidden, which is trainable, which is optimized during the training process. In fact, it can reduce training, development, and deployment costs because it's a single but complex network. The limitations, the models are very complex, so often combine different architectures like diffusion models, GAN models, and I don't know what. So it's more challenging to train such models. And higher computational demands, of course. And overview of neural TTS models, just to show you the boom in different models, TTS models from 2016, WaveNet, and this is and 2022. So from 3 years ago. So there will be many models here, of course, from that time. Okay, so we now switch to some, let's say, advanced topic. It's voice cloning. What is voice cloning? Voice cloning, or maybe sometimes you can see TTS personalization. It's a TTS technology to synthesize speech in the voice of a specific target speaker. That's correct. But the goal here is to generate synthetic speech that matches the timbre, the prosody, and style of the target voice using only a small amount of reference audio. You don't have hours of speech of a given speaker. You just can have, I don't know, 5 minutes or maybe 10 seconds of speech, and you want to clone his voice. Yeah. In fact, we can use two strategies. We can use few shot strategy, which typically requires few minutes of reference recording, and the system is fine-tuned, adapted to the new voice through additional training, short-term training, but we must train the model, fine-tune to train the model to this new voice. Few shot training or few shot strategy. Zero shot strategy. One can clone a new voice using only a single short reference sample, just seconds of speech, and no additional training or fine-tuning is required. It means that the system generalizes to new voices instantly by using the reference sample during inference. You don't train the system more, but you have just short reference and you use it during inference, reference during inference. Yeah, very often you use pre-trained models here. The models are pre-trained on speech data from many different speakers. In this way, you can then generalize the model to a new voice when you have just a small amount of the new voice. Otherwise, it's not possible. We call this large speech language models, LSMS. Something like analogous to LLM from NLP. And also we can use some large text phoneme models which are utilized for improved phonetic and coverage, like, phoneme level BERT or something like this on a phoneme level. You can use it, and it's good to use it for voice cloning. So very simplified scheme. We have some network, and when we try to clone the voice, we had to pre-train the model, as I said. So we have some many speech waveforms which were available on the internet, let's say, in the given language, and we don't know the transcriptions of these recordings, right? This is self-recording, self-training process, not supervised. We also have many texts. These texts do not correspond to the waveforms, but we have many texts, and we can train a model on text. We train the model on audio and separately on text. This is the first stage. In the second stage, we can have some, data typical for TTS. So we have a pair of text or phonemes and the corresponding waveforms. And we can fine-tune the model, which after the first stage, the model knows, let's say, how speech looks, because he It saw many speech waveforms. It saw many texts. So I personalized the TTS system. It knows how speech look and how the text look. And in the second stage, we now show the model what is the correspondence between the phonemes and speech waveforms. Okay. And in the third stage, we have just one single reference of a target voice, and the system generates any speech from any text in the target voice. Okay, so this is voice cloning, very simplified. Some known popular, let's say, TTS systems that are good at voice cloning are your TTS, XTTS, Natural Speech 2 and 3, Speech T5, Vol-E, StyleTTS 2 is also somewhat good in voice cloning, and many more maybe. Just as an example, I will show you Speech T5. Speech T5 is a very capable model from Microsoft. It's a unified multimodal model inspired by T5 from Google. T5 was a transformer model pre-trained on NLP data, NLP purposes. And this multimodal Speech T5 enables to model speech and text, and maybe some other modalities too. In fact, it uses two-stage fine-tuning. In the first stage, we tune it on large-scale TTS-friendly speech-text pairs. We have a pre-trained model, first stage, and the second stage is fine-tuning, and we can use as many TTS-friendly data, phonemes, and waveforms from many speakers to fine-tune this model. And the second stage is to use just a short recording, 1 to 5 minutes, of target speaker voice, and fine-tune the model to this target voice. So in fact, it's a few shot voice cloning with this model. This model is very interesting because it supports multiple speech and language tasks, not only text-to-speech, but it also supports speech-to-text, speech recognition, speech enhancement, speaker identification, and voice conversion. It depends on how you train and how you fine-tune this model. So for TTS fine-tuning, we use text at the input, and there is a MEL spectrogram at the output, and it's autoregressive framework, so these spectrograms are then fed in the input of the decoder, and it's in this way they can generate the whole speech. And yeah, it works for speech, for voice cloning, as I show you in a minute. The second example of a voice cloning system is Vol-E, again from Microsoft. It's a very special model in that it's a neural codec. It uses a neural codec architecture. So it generates, sequences of audio tokens instead of directly predicting acoustic parameters or spectrograms. It works on similarly as LLM, which generates some text tokens. Here, some neural tokens, neural codec tokens are generated. It was pre-trained on LibriLi dataset. It's English dataset from more than 7,000 speakers, and the speech is around 60,000 hours of English. And they say it is possible to clone voice from a 3-second reference clip. So we need just 3 seconds of the target voice here. Yeah, and when we use, also some multilingual data, it can work on multilingual basis, and then it's called Vol-EX, not Vol-EN, but Vol-EX. Okay, so few short voice cloning example. I will now show you, I'm sorry, in Czech only. These are Czech presidents, and we used speech T5 models. Speech T5 models, it means we fine-tune them with 5 minutes, approximately 5 minutes of their speech. And this is original speech of Václav Havel. I believe you may know this name, our first Czech president.
To všechno tedy souvisí se svobodou. A já jsem to už víckrát provedl, že jsem ten...
So this is the original, and this is the synthesized version, voice clone.
Tuto větu jsem nikdy neřekl. Byla vygenerována pomocí počítačové syntézy řeči. K vytvoření té...
This is our second president, Václav Klaus, the original.
Vážení a milí spoluobčané, dovolte mi, abych vás v první den roku 2012 co nejsrdečněji...
And so on, and this is the voice cloned version.
Tuto větu jsem nikdy neřekl. Byla vygenerována pomocí počítačové syntézy řeči.
Okay, next one. This specific voice and style, especially.
Nikoli lidé, kteří se vynoří z neznáma a řeknou, že sice nic nedokázali, ale že
This is the synthetic version.
Tuto větu jsem nikdy neřekl. Byla vygenerována pomocí počítačové syntézy řeči. K vytvoření této nahrávky byly použity
And this is our current president.
Nový rok jsem vždy vnímal jako den plný očekávání, že časy, které máme před sebou, budou...
And this is the synthetic version.
Tuto větu jsem nikdy neřekl. Byla vygenerována pomocí počítačové syntézy řeči. K vytvoření této nahrávky byly použity hluboké...
Another example is of zero-shot voice cloning. Previously, what you heard was in Czech. It was using our implementation of Speech T5. This is completely generated with XTTS system. On the left, there are some Czech people and Hurvínek. On the right are, So this is the original voice of Donald Trump.
Thank you, Klaus, very much. It's a privilege to be here at this forum where leaders in business
and so on. And this is its cloned voice in English. No. We can try German version of Donald Trump.
Dies ist ein Beispiel für Sprachsynthese. Für die Erstellung wurde nur eine kurze Aufnahme meiner Sentenz. Dies ist ein Beispiel.
Yeah, we have also a version of Chinese. It could be helpful, with negotiation with China, So, yeah.
这是语音合成的一个例子，仅使用了我声音的一小段录音来创建它。
Is it intelligible? Yeah. I don't know why the English version is not working. Yeah, no. Joe Biden, original.
My distinguished guests, my fellow Americans, this is America's day. This is democracy's day.
Okay. Will it work in English? Yeah, maybe.
This is an example of speech synthesis. It was generated using just a short recording of my voice.
And Chinese.
这是语音合成的一个例子，仅使用了我声音的一小段录音来创建它。
And do you know Hrynek, the famous Czech character? It's loutka. Pupil. Yeah. I can show original voice.
Že se holubovi vůbec nepodobá. No, že každý vypadá jinak, to dá rozum. Jak by se od sebe rozeznali, kdyby vypadali stejně?
So, English version.
This is an example of speech synthesis. It was generated using just a short recording of the voice of Hervenek.
And German version.
Dies ist ein Beispiel für Sprachsynthese. Für die Erstellung wurde lediglich eine kurze Aufnahme von Herveneks Stimme verwendet.
Okay, so these were some examples of voice cloning. Yes, just a list of some useful data sets which can be used in speech synthesis and are available as open source. So you may know LJ speech is very popular, Libri speech, Libri TTS, and so on and so on. Okay, so we are close to the end. So something about future directions, and I will show some examples of our projects. Since the main goal of TTS is still very easy, let's say, synthesize high-quality speech, so the future directions will be towards improving synthetic speech quality. Still, there is some room for improvement. What's apparent is that the modern model-based approach, based, of course, on deep neural networks, greatly improve the quality, but still there are some as I said, some room for improvement. But I don't expect some change in the direction. I believe model-based approach will likely continue to drive future progress as today. What can be improved? The key to synthesize a very good speech is to use good, powerful generative models, okay? So there is some space to improve these generative models, to look for some other, frameworks and principles. Better representation learning. Good text and speech representations improve neural TTS quality. It's a known fact. You can represent maybe better the input text. You can use some more sophisticated, pre-trained models from many texts and phonetic knowledge and so on. So learning powerful representations remains a key challenge. Robust speech synthesis. Some early advanced neural networks like Tacotron suffered from some errors like, something like hallucinations or something like skipping or repeating words. It's okay now. It's okay, but still there are some problems which can be addressed to robust speech synthesis. For example, style TTS2 model, which is popular, it has some problems with generating short sentences, and maybe some other models too. When you have, for example, data set which consists of longer sentences, and then you try to synthesize shorter sentences, one-word sentences, it could be a problem. So Improving in general, improving generalization to unseen text and domains is key for robust speech synthesis to enable the model to synthesize text, also diverse text which were not available during training, for example. Expressive, controllable, transferable speech synthesis. It very often depends on effective modeling on variation in speech. You would like the speech to be diverse, to be rich in variation, and today models typically do it implicitly. It means the resulting speech is really natural, is expressive, is varied, but because these properties are implicitly hidden in the model, they are very difficult to control, to change to some other, modalities and some other styles and so on. So research on so-called disentangling, it's a difficult word for me in English, disentangling content, prosody, style, even noise, when you don't have acoustically pure, clean recordings, to be able to split these, components of the speech signal and control, change these characteristics separately. It could be benefit. So designing better methods for expressive, controllable, and transferable speech synthesis remains an open challenge still. More human-like speech synthesis. It's not, today there are some conversational data sets too, but still the main focus is on, to use formal reading styles like audiobooks and so on. And this formal reading style is quite different from common casual speech. There are no pauses, there are no repeats, no speech changes, no emotions. There are not natural errors which human naturally uses during speaking. So the real human speech is still different from the majority of data sets. It often uses casual, conversational, emotional, and spontaneous speech and so on. So better modeling of these styles of speech is key for improving naturalness of synthesized speech, can say. And there is also something like effective speech synthesis. The key to effective speech synthesis, effective TTS, is the optimization of TTS pipeline. We can look at it from different aspects, like data efficient TTS, because many low resource languages lack sufficient training data. We don't have training data for some languages, but we have many data for other languages. Mainstream English, of course, or maybe for some languages which are close to the language we don't have the data. So unsupervised, semi-supervised, cross-lingual transfer learning can help overcome this problem. We can use some knowledge or some data from other language for the language which we don't have the data. Voice cloning, adaptation conversion, few shot, zero shot synthesis with small amounts of target voice in the given language can help us. Parameter efficient TTS, this is the next step. After we have after we have very high quality neural networks, it would be the next problem, how to use these very quality networks in some other not so powerful devices. So you know that modern neural networks use large models, much more than 1,000 million parameters, maybe more, and this is a problem in real world applications. These large models cannot be used on mobile or IoT and other low-end devices which have not sufficient memory and power. So designing compact, lightweight models is critical for these applications. And what is today also very important is energy efficient TTS, because training and running high-quality TTS models require significant energy and result in high carbon emissions, so improving energy efficiency is essential for other, extension of neural networks to some other products and so on. It's today also a significant point of view. Okay, so this is the end of the, let's say, my talk, my presentation, and still I have here some 3 examples of our project from our department. Some will be in Czech, some in English, just to see what we are doing in this area. I will start with something like Save Your Voice project or Voice Conservation project, which was a project for patients before total laryngectomy. What is interesting is that this project started before neural networks were used. So we performed something like voice cloning using technologies like unit selection in that time. The goal was clear, to preserve the patient's original voice using TTS and an external device, because the patient that undergoes total laryngectomy is not able, unfortunately, to speak in his voice or her voice anymore. Total laryngectomy is a disease, oncological disease at the vocal folds, and they had to remove the vocal folds to save the life of the patient, but the human can never speak again using his or her voice. So we recorded these patients before surgery, and we prepared a personalized version of the TTS. So just one example in Czech. This is the original voice.
Nejvážnější zdravotní komplikace během oslav postihla 40letého parašutistu.
And this is the synthetic voice.
Posloucháte ukázku mého syntetického hlasu. Myslím, že se hodně podobá tomu mému. Je to první verze, která...
So on. What is interesting is that this was not neural network. It was unit selection speech synthesis. But I don't know, 2 years ago we were contacted by a lady from Singapore, which found us, website and so on, and she asked us if we were able to conserve, to clone her voice. We tried, and we used neural networks. It was 2 years ago. So this is the original voice, English voice, with a Singaporean, I would say, accent. This is the original.
They should live in modest circumstances, avoiding all conspicuous consumption.
The lady had some problems with speaking at that time because her vocal folds were not good. And this is the synthetic version.
Hi, you are listening to my synthetic voice right now. It was generated with the help of artificial intelligence, but we believe it sounds mature. What do you think?
So, so this was this project. Another project was also interesting. It was intelligent technologies for enhancing air traffic safety. We tried to innovate air traffic control training. Traffic control, I mean the operator, the human who is training to be, air traffic control in his job. And it was, in fact, a voice dialogue, ISR and TTS, for communication between ATCs, air traffic controllers, and pilots. And the goal was to make training of these people more diverse and realistic by exposing trainees to accented English as spoken by pilots of various nationalities. You may know the pilot voices in airplanes. I barely understand them. And the TTS part in this project was about the creation of virtual multilingual pilots speaking in the accented English commonly heard from international pilots. It was in TTS, it was an in-domain text-to-speech because we use primarily, aviation phraseology. And the accents the pilots with Czech, German, French, Serbian, and Taiwanese accents were created during this project. I have an example here of a Serbian pilot.
Cleared for departure runway 2 for Genex 535.
A German pilot, a woman.
Praha, good morning, German wings 935, flight level 360, inbound it is.
And a Taiwanese pilot.
Praha Jet Cargo 7. 444, requesting flight level 350.
Okay, so it was an interesting project for us. And the last one, very short, Karel Gott, sorry Honza. This is the last example of how can speech synthesis can be used in public, public space. 2 years ago, there was, we have a Czech radio, and it had 100th anniversary of broadcasting, and we were asked to create a voice of legendary Czech singer Karel Gott. I don't know if you know this name, maybe some German people here could know it. Bean Maya, he also had some, songs in German, never mind. In fact, we prepared a narration of his autobiography broadcast, and it was broadcast daily on Czech radio, and also it was released as an audiobook. It was first ever use of TTS in a dramatic work, at least in the Czech Republic, and with more than 1 million on-demand plays, it was the most listened to literary and dramatic piece in Czech radio history. So I now show you a short example of synthetic voice of Karel Gott. It was post-produced in Czech radio. It was not, direct TTS, but it was somewhat post-produced, and there was some music in the background. So this is the example of the final speech.
Když jsem v roce 2015 onemocněl, zatrnulo mi, že svoji knihu vzpomínek nestihnu dokončit. Každou volnou chvilku jsem rozmanité vzpomínky pilně a všemožně zaznamenával. Občas jsem měl pocit, jako by to bylo včera. Někteří aktéři z mé knihy mohou tvrdit, že to přece bylo jinak. Já si to pamatuji takto, po svém.
Okay, that's it. Thank you.
Yes, I just have to switch off.
Do you have an experience or an idea on training TTS on a data that is labeled by ASR systems? When we have noisy labels. For example, for low resource scenarios, when the training data is labeled by an ASR system.
Okay.
Do you have any experience or?
In fact, the voice of Karel Gott and some other voices, there was no transcription of these audios, of these recordings. So we used ASR to transcribe the speech into phonemes. But there was some check of this. We checked the transcription and correct them.
So without this correction, do you have an idea how we can revive from these errors, or?
We tried it, but I have known the numbers how bad it was. It definitely worked, but there could be, some problems, especially when, there are some consistent problems with ASR. So in this context, there could be some problems also, I think, in TTS, because the transcription is not good. And maybe some phoneme and its context could not be learned good, in a good way, because the transcription is not good.
Thank you.
But, the foundation models, the pre-trained models like for speech T5, the principle is that you don't have transcriptions and you just, so for the first stage when you utilize many data just to learn how speech signal looks, it's good. But then you have some fine-tuning stage, and in fine-tuning stage you need to have the classical pairs, phonemes and waveforms. But for the first part, not.
Just another question. You have a lot of experience on Czech. I don't know if there are a lot of lexical variations in Czech or no. In such scenarios, for example, when we have in the written form, we have many forms,
okay,
but the pronunciation almost is the same. For such variabilities, you have you face such variabilities, or how we can manage such cases?
If I understand well, in Czech there are many forms of a single word. That's right, because it's a highly inflectional language. But we have rules that are able to phonetic transcription rules that are able to catch these inflection forms. So it's not a problem for, let's say, nice Czech words, but the problem is for, some irregular foreign words which are not, inflected as we expect for Czech words. So yeah, this is the problem, and we have to use some dictionary of exceptions to catch these exceptions.
Thank you.
Yeah.
I think the models that you're referring to are mostly for a single speaker, I guess, speech synthesis. What would need to be changed in some of those models for it to be like multi-speaker, or?
It's not, maybe.
In some of the models that you described, they were mostly single speaker speech synthesis. What would need to be changed for, like, let's say, conversational or multi-speaker synthesis? And I guess why is that problem a little bit harder when I feel like some of the recent models haven't been able to go past 2 speakers in like a multi-speaker speech synthesis problem?
So your question is how to use multiple speakers with some models. I think a bunch of today models is able to use multi-speaker data. You just need some, some conditioning on the multiple speakers, some speaker ID or something like that. StyleTTS, for example, doesn't need even the ID, but it, uses the style, and the style is computed from the waveform, and the style is different for each speaker. So in this way, it's implicitly, the StyleTTS can differentiate between speakers, in fact. And I believe other models like WITS and some other models, they just need to know that this is another speaker, this is a different speaker. So there are IDs for these speakers, and they are modeled together with these IDs, and the ID is a conditional input to the inference then, and the model is then able to synthesize the speech in the concrete speaker. So most model, I think that there is nothing new, just to use this ID for different speakers, I believe.
I guess I was trying to ask more about like conversational speech synthesis, like in a single, I guess.
You mean something like LM Notebook podcast and so
yeah,
on?
maybe.
So, and the question is how to use the multiple speakers?
Yeah, like what would need to be changed in like the models you showed us to have like a conversational speech generated?
In fact, I don't know. I think, again, you must have more speakers in your data. You must know which speaker was, speaking at what time. And that's it, I think. Definitely, I think you have to the training should be mixed from two speakers, not just one speaker and another speaker, because the style is different, completely different. I believe you had to record people conversating, and you then have to know where one speaker and the other speaker speaks in the recordings. I believe. I don't have any experience with this.
You mentioned the disentangling of the latent variables for voice cloning. How would you go about that? If there are these variables that the model can capture, it can obviously tell the difference in these variables from a speaker, the little Czech puppet. It can tell that those have higher tone and versus whatever Donald Trump has lower tone, and there are all those variables. Would you just need different labeled data that has specific stuff like that, or could you? I know the neural network is kind of impossible to dive into like that. I don't know.
Yeah, I'm sorry. I have no experience with changing different aspects, different properties of speech. I believe you don't. You have to, again, you must differentiate between these properties at the level of the training data to try to learn as best as you can the characteristics of different styles and people, I believe. And it's nice that if you have during inference some possibility to emphasize some characteristics or lower or higher, yeah, but I'm sorry, I can't be more specific because we haven't tried this one.
Maybe I have one question. Oh, sorry, Marek. Oh, thank you. Go ahead.
You were saying when you were talking about those retro machines that were creating voice, and also later you were talking about prosody. Mm-hmm. Are there any analytical measures to concretely say how good is the prosody in the language? And especially when you were mentioning the retro machines, right? I mean back in the days it really had to be sort of statistical, models, right? With the hand. Do you know of any specific measures? Because later for example when colleague was saying, right, I can imagine that if you would have such a measure of prosody, yeah, right, then for example Donald Trump's prosody would be very significant somehow feature. Right?
Yeah, in fact, when you evaluate speech, you evaluate also prosody and evaluate it using some naturalist metrics like MOS and so on. What is, of course, when you train a neural network, you can have some pitch-related loss, which is, you can imagine that each training sentence has some F0 contour, and you also try to generate the F0 contour, and you are trying to match the ground truth data using some measure, like some simple measures, include an instance, I don't know. So it could be, and sometimes it is, used during learning inside within the network. But I don't know about some. Yeah, and you can, of course, you can explicitly extract, F0 contour, for example, from synthetic speech and from ground truth, and you can measure whether the contours are the same. But sometimes they don't have to be the same, but it still sounds very good, very nice. So this is the question whether this you should compare some single aspect of synthetic speech, because it could be very human speech is so complex and so rich and so good that there are many it's one too many problem, of course. So one text could be really reasonably nicely pronounced in various, and prosodically pronounced in various ways, and it's okay. Yeah.
Okay, so
to be sure if I understand, let me ask like a last question, because what I have in my mind is like, is it you know, of course, it's maybe hard to, you know, like mimic a specific person, right? But for example, if we would have a lot of data of Polish speakers and Czech speakers, right? I mean, I can imagine that there could be possible, like not like voice cloning, but like style cloning, right? Like the prosody of the language, right? You know, like I'm trying to like imagine how would Polish language sound, right? But with a Czech accent and vice versa, right? And that would be exactly this like curves of prosodies, right? Or like sort of this like shape of the, I mean, like prosody would be the notion to look for in the data to like try to make such a you know, style accents transfer.
Yeah, so you would like to preserve the accent in the synthetic speech, or I don't understand now?
No, I mean, I would like to imagine myself, you know, like there would be, you know, agent system, you know, a system can give my voice, but,
okay.
You know, in Polish language, but then I would like to, you know, like just add this like sort of like accent, like the singing vibe of the Czech language, right?
Mm-hmm.
Right, from the point of view of Polish speakers, Russian speakers, right, they're like singing, you know, Czech also like singing, right? Like we call it like singing thing, right?
Okay.
So I mean, is it?
I think there are some approaches to, you know, accent to preserve accents in a speech, or to remove accents in speech, you know, because sometimes some people, me is a good example, have a strong Czech accent in English, and there are two possibilities: to make my voice in English exactly as I am speaking, so to preserve the accent, or no, I would like to be better in English, so to remove the accent. So to use my timbre, to use my prosodic characteristics, maybe other than accent, and to use accent from some, I don't know, average British or American guy, or some concrete people, concrete speaker maybe. So yeah, I think two possibilities, and there are studies about this phenomena. Yeah.
So. Yeah. Just to recommend, there is currently a US government program under IARPA that is called ARTS, and ARTS is about like obfuscating the speaker identity, but they also have one task about making sure like that the accent is not recognizable. So that's exactly what they want. They want to change a Czech accent in English for American and vice versa. So well, we hope to be in the project. We are not. We didn't get the funding, but definitely there will be papers occurring with the funding of the project that will be mentioning this.
In the air traffic control project, the aim was to preserve the accent, because it was the aim to listen to diverse English speech from many accent you know, with many accents from different languages. Yeah. So
I had yeah, okay.
Thank you. I have one question regarding like opposite. You said about not healthy voice that were changed into healthy one, but did you heard about a project or a publication that did the opposite, like trying to synthesize a voice with sore throat or with Parkinson, or just for the sake of, for example, training speech recognition, or
I don't recall now a concrete project, but I think there are some studies and there are some projects about this phenomena. Yeah, but most projects try to do the opposite, of course. And what is interesting is that today, our experience is, okay, we can deliver a voice to a person who cannot speak in his voice anymore, but the problem is that he or she must type text and to synthesize it. So there are some approaches how to make this more user-friendly. The vision is to have, and it works, to have some sensors in your brain, and it works, but it's not so good for people to have sensors inside your head, in brain. So there are some attempts to use something like, caps, or some not inside your brain, but sensors around your skull, and to try to convert your thoughts in speech. So it's dangerous, but it could be very good way for these people how to speak again, not typing. Or maybe something like, to use their voice or something, how they speak today, this one, and to convert it to regular speech. That would be something like, when you, there will be some delay, of course, because ideally you should remove the original speech and to convert it to normal speech. It's quite difficult, but there are some I believe there are some studies about this. So it would be very nice and useful for these people.
I wanted to ask about the synthesis in dialogue systems. So when you have a dialogue system, for example, with customers, you should adapt the way the TTS operates depending on the speaking style of the customer. So if you have a youngster that is speaking like this, like fast, and with all these new words, and then you have an older person, maybe with hearing impairment that goes very slowly, you should be able to adapt the TTS to the person that it is talking to. Did you do any works in this direction?
We haven't tried, but it's a good idea. I think it's an ongoing project somewhere that it's good to adapt your speech or the speech of the dialogue system to the needs of the user. So it's.
Okay. Anything else, guys? Yes.
Yeah, I'm just a little bit curious about your project. So did you train a model from scratch, or you choose an existing model and fine-tune it?
Which project?
The first one.
You mean the learning or total laryngectomy project? Yeah. The Singaporean lady, I showed the examples. It was just, 30 minutes of speech. So we used a pre-trained model, VCTK, or Libre speech, I don't know now, but we used a pre-trained model. I think it was WITS model, and we fine-tuned it to the voice of the lady. Okay.
Yes.
I have a question regarding the TTS diversity. Nowadays, I think many TTS system is not diverse. As human beings, when we speak, we probably cannot speak even if we speak the two identical sentences, but in pronunciation, we probably different from that. So it's like we have more diversity. However, the TTS is not. Is there any the future trends or the possible track to improve this TTS diversity, especially for the emotional, like human beings, we have different emotions even for the same text, we probably have a different. Is this the diversity missing is because of the lacking of data or another reasons, or what is your opinion? Thank you.
Just my opinion, because I don't have enough experience with conversational speech and diverse speech, but I believe today it's mainly about data. So if you have very rich data and you can work with the data, you know the data, then you can you can have more diverse, or you can have more models that are able to generate more diverse speech, I believe. So I believe it's about data, and of course the models must be able to catch these, complex, diverse modalities. So but I believe the data is the first step. Because as an example, when we talked about unit selection speech synthesis, it was quite nice, but it was for the specific style. And when new neural networks paradigm started, we and maybe some other teams also too tried to use the data sets that were recorded for unit selection. And it was nice, but the jump in quality was not so obvious because the data was, prepared for previous generation of speech synthesis. It was not so diverse. And apparently, new neural networks can work with much more natural, much more, live, I would say, speech recordings than unit selection. So if you had a database, audiobook, for example, which is diverse in this sense, and you use the same neural networks as for the previous generation data sets, the neural network will, for the audiobook, for example, it would be quite better just because you had data which were more diverse, more human, more natural. Yeah? So I believe this is the same as if you would have much more diverse data for training the same neural network, the output will be more diverse.
No more questions. Thank you, Jindra. And this is closing our 6th day, so have a good evening. The weather is not terribly good, but there are definitely things to do in Brno also when the weather is not good. And see you tomorrow in the morning.